This is the video for 7.1 lesson. I'm just starting with showing the new assignment sheet here that you hopefully got. Today we're talking about an introduction to similar polygons, but remember that tomorrow is still your test on Unit 6. So you just have to kind of know that none of the same stuff that we go over today will be on it. You could actually wait to do the homework till Wednesday night even if you wanted to, just to study tonight a little bit more for the test. Homework is listed a little bit different this time. I didn't change this, but really you can just use the bookwork or the packet that I still printed out. It just should match all of the same bookworks that are on here. But if you have a question on anything, I can clarify. All right, so next quiz is not till the following Friday, which is the 3rd, and then finally we have a test on Wednesday the 8th. So that's a little bit about the schedule. Let's get started here with similarity is our new unit today, and the learning targets for today and the rest of the week are included here, starting with what are we going to talk about, like what does similar even mean? I know that and you know of the word similar, but in math it means something more specific. We're working with dilations again a little bit more today. That was back from Unit 2, and then working with proportions and how to solve problems that will deal with proportional sides and also congruent angles. But we'll bring all of that back today from the Unit 2 stuff, like we're starting with right now as we start on the back page here. So it starts with, we have 2 columns here, talking about isometric. I know that that word sounds like new, but it's really going off the word isometry. And we know that isometry meant that none of the angles change, none of the side lengths change. All that happens is like you can translate it, you could like move it, you could reflect it, rotate it, and all that would change would be either the placement of the points, like the location of them, or even the orientation could change potentially, but none of the size would change. So this triangle here, we're about to reflect this over the y-axis, and as we do that, we're going to notice that nothing's going to change other than just the position of this triangle, like, or where it's located. So let's go ahead and reflect this one. So if you remember how we do a reflection, here is first of all I'm going to draw in my y-axis here, and there's a highlighter here to represent what I'm actually reflecting over. And let's go ahead and move each of those points. So you just count from each point to the line of reflection and go that much more in the other direction. So if it's just 1 point to the line of reflection, go 1 more. This one is 1, 2, 3, 4. So we're going to go 1, 2, 3, 4 and put a dot. Same thing on this one, just 1 over, so 1 on the other side. And then you draw out this new triangle, and that is what the reflection should look like. So we just did a reflection over the y-axis. We're going to fill out this whole first column first, and then we'll go over to the right and fill out the right side, because we want to kind of compare the two when we're done, but all of this kind of goes together. So we're going to fill out some of these blanks just to remind ourselves kind of what happens here. Okay, so the first blank says an isometry is a transformation in which side and length and angle measure is preserved. That just means it's not changing. Everything stays the same with the side lengths and the angle measures in that original figure. And you could name this if you wanted to. Remember, if this was triangle ABC, remember we used to use these little apostrophes that stands for prime. So A prime, B prime, C prime shows that you just did a transformation. Okay, and it says when an isometry is performed, the figure and its image are congruent. So those 2 triangles there on the top, both of these are congruent to each other because they have all the same angles, all the same side lengths. All we did was just move it to, reflect it. So we moved it and changed its orientation slightly. Okay, and so then just to define congruent polygons one more time, it says 2 polygons are congruent if and only if there's 2 things that have to be true. The corresponding angles are congruent, and the corresponding sides have to be congruent. So now since we labeled these triangles up at the top, A, B, and C, and then A prime, B prime, C prime, let me just write down which ones are corresponding, right? This word does not mean corresponding angles like when lines are parallel. Those are different. This is just talking about which ones match up. So like angle A is congruent to angle A prime. Angle B is congruent to angle B prime. And angle C is congruent to angle C prime. Okay? Same idea with the side lengths, except now we're going to say which sides are matching up. So A to B, segment AB, remember you put the bar on top, we say is congruent to segment A prime, B prime. Same thing for B to C, it would be congruent to B prime, C prime. And finally, A and C, segment AC, is congruent to A prime, C prime. So as a result, if all three angles and all three side lengths are congruent, then these are again corresponding. We would write triangle ABC is congruent to triangle A prime, B prime, C prime. So we did a lot with congruence all in unit 4 when we worked with triangles that were congruent to one another. And we did like ASA, SAS, and so on. All those different triangle congruences that we did with the proofs. So we are going to have a little bit with proofs in this unit as well, but not today. They will come kind of later this week. Okay, so now that's everything with like it's almost like a review. We're going to come over to the right side now, and we're going to practice doing a dilation. Still a review, something we did back from Unit 2. If you don't quite remember that, it was on the final exam as well. And then we'll talk about how it relates to this new idea of similar polygons. Okay, so we're dilating from point 4, 5. So first, let's find that point. It is the point of this triangle that we're kind of doing it in terms of. I'm going to label these points just so we can talk about them. So letter D here, E, and F down here. So when you do a dilation from a point that's on the actual figure, that point now becomes also E prime. It doesn't move at all because that's where you're dilating from. So remember, if it's a scale factor, in this case of 3, we're going to triple what the distance is here. So if I'm going from E to D, or E prime to D, that's 1, 2, 3, I'm going to need to count that 2 more times because I want a total, like I want to multiply that 3 times. So that's once, twice, 1, 2, 3, 3 times. So that puts my new D, or D prime, at negative 1, 2, 3, 4, 5, and positive 5. So negative 5, positive 5, that's where this new point is. And then you do the same thing with letter F. But to get from E to F this time, I have to go down and left. So I'm going to have to keep doing that 3 times. So I'm going down 1, 2, 3, 4, and left 3. 1, 2, 3. So I'm going down 4 and left 3. I'm going to do that 2 more times because that was once. So 1, 2, 3, 4. I went down 4 and left 1, 2, 3. Do it 1 more time. Down 1, 2, 3, 4, and left 1, 2, 3. So your point for F prime should be sitting at negative 1, 2, 3, 4, 5, negative 5, and negative 7. Okay, so in case you're wondering, like, did I plot it correctly? That's where that point is. You can now connect your original, or like this new triangle that you just made, and you will see some overlap. That's because we kept it, point E, fixed. We didn't move that point. And so that's what this new dilated triangle looks like. Now, if we were talking about these 2 triangles, they're definitely different sizes now. There's a smaller one, DEF, and now this 3 times as large one, D prime, E prime, and F prime. So what we just did is we stretched this out because it was a scale factor of 3. So let's go ahead and fill out some of these, and then we'll talk about what these are called now. So dilation is a transformation that stretches or shrinks a figure to create this thing called a similar figure. We talked about it then in Unit 2 when we talked about dilations, but now we're really going to talk a lot about similar figures. And specifically, when it says non-isometric or non-rigid, you don't have to know these words so much, but that's like the mathematical word for what we are actually doing. So when you do a dilation, it is a non-isometric transformation because it changes the size and the shape. It's not isometric, or it is not an isometry. And so that's what happens here. And it says the scale factor of K, which we call K, of a dilation, which in this case is 3, is the ratio of the side length on the image to the corresponding side length from the original figure. So if I want to calculate this for a second, let me go up to the top, and I want to compare my sides. From D to E, that was 3 units. But when I count from D prime to E prime, that's a total of 9 units. Okay, I could do the same thing from D to F. D to F is 4 units. Oh, sorry, I wrote 5. I meant 4. And then if I count how many units this is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, if I go from 4 to 12, that is 3 times as much, right? So 4 times 3 is 12, and that's why these numbers make sense. So if I go down here again, this is what a ratio looks like. We talked a lot about image over original before, and now we're kind of doing a lot more with that. So image is d prime over e prime because it's always the one that you transformed, and then over the original is de. I could technically do any of the side lengths, though. I could do this, and I could do 9 over 3. So that's how I see that my scale factor is 3. That's one example. But I could have also done d prime f prime over df, and I would have done 12 over 4 and still gotten 3. So no matter which ratio whichever side lengths you use, as long as you use the correct ratio, image over original, you'll always get the same scale factor. In this case, 3, because that's what we multiply. So then whenever you're working with dilations, they're going to create similar figures or similar polygons. And here's what's true about polygons that are similar. It says 2 polygons are similar if and only if. There's 2 things that are still going to be talked about. Still talking about angles and side lengths, just like we did for congruent polygons. It's just these were both always congruent. These ones, the corresponding angles are still congruent. That's not changing. So the nice thing here is angle A is still congruent to A prime. Angle B, I'm sorry, it wasn't A. I'm mixing up my letters. It was D and D prime. E is still congruent to E prime. And F, angle F, is still congruent to F prime. Okay, so that's what we still have no matter what, whichever type of polygon you have, similar or congruent, the angles don't change. But what does change is that the side lengths are no longer congruent. They are this word called proportional. And that's why we're able to take a ratio of the image over the original to do this, because clearly the side lengths are not the same. You can tell the sides are much different because they're much more larger when you do the scale factor of 3. But they are going to be proportional because, like we saw with the 9 over 3, I just showed you the 12 over 4. We could also find the other side, but it's a little bit harder to find this side because you have to use Pythagorean theorem or distance formula to find those. So just writing down the proportions will do that. So d prime over e prime, d prime e prime over de would equal the same thing if I did d prime f prime over df, and would also equal, what side am I missing? E prime f prime over ef, right? That's all 3 of those sides accounted for, and that just means that no matter which one I use, I'm always going to get 3 here in our example from above. That's my k. So in this case, I got 3 for my answer. It's not always going to be 3, but it's whatever is that k. Now this is how we write the new notation, similar to this, but we want to use the word similar instead of congruent now. So we say triangle DEF, and then it's just one of these squigglies. This is how you show similar instead of congruent. So DEF, and this is D prime, E prime, F prime. All right, and so we're going to do a little bit more with that, especially all this week. But just to help you out with a couple of the questions that would be similar to what you have on the homework, I'm going to go through a few things on the next page. But the rest of this practice you can definitely try out, and I'll also go over some of it tomorrow. All right, so let's go to the back page here, and just kind of reminding, a lot of it should look familiar because we did a lot in Unit 2 when we did dilations, specifically working with scale factors, so hopefully you still have to remember how to do that. We talked a lot about like when a dilation is an enlargement versus a reduction. Those are pretty simple to see too. The only new part really is this. Writing a similarity statement, name all the congruent angles, and list all the parallel sides. We don't always list parallel sides, but that just means once you did the dilation, what sides kind of match up. Okay, so we'll do, we'll try out one of the ones that are down here, number 2. For this one here, I'll kind of let you guys try this one out, just like kind of doing the dilation and then seeing, because we just did a dilation on the front page as well. So it's the same idea, except now it's a 2 instead of a 3, so not very different. Still using a point that's, in this case, not actually on the actual triangle, so you're still going to like find where that point is and just measure everything in terms of that point. So going from, let's say, from this point of from the point of dilation, you're going to say, okay, I'm going down 1 and right 2, but since I'm going for a scale factor of 2, I would go down 1 and right 2 again. So let's say I'm going to just do 1 for you guys. A prime would be there at 3, 0. And then you could do the other ones and then draw your new triangle, which should look double in size. And then you would write the similarity statement and so on. So I'll let you guys try this one out just so that you know which one it is. It's definitely enlargement, and specifically K, since K is greater than 1 because it's 2. And for part C, all you're doing is writing the similarity statement of the triangles. So this is pretty simple, whether we have the triangle drawn out yet or not. It's just saying that those two are similar to each other, and name all the congruent angles and list all the parallel sides. So I'll let you guys finish this part, but you're literally just writing out all of those side angles that match up. And for the sides, you could say something like side AB is parallel to side A prime B prime, and so on. You would do all the others. Okay, so let's try one of number 2. We've done something similar to this again before in unit 2, but just kind of bringing it back some more in this unit. We're determining whether the dilation from figure A to B is a reduction or enlargement, and you're finding the scale factor and the values of the variables. So starting with, it doesn't matter, let's do, just because I want to go over like an easier one. This one, letter C, definitely is much tougher because it has a quadratic that we won't necessarily be working on for the entire time. I'm going to just do the first one because we haven't seen a reduction yet. From A to B, you can clearly see this is a reduction in size, right? Because it's getting much smaller. Let's see how the numbers are changing. So you match the sides up, and the only side I know is this long side here of the rectangle, or it looks to be a rectangle, is 2, and the original one was 6. So you're doing 2 divided by 6 for image over original, and this would be 1/3. Okay, so my K value here is 1/3, or my scale factor is 1/3. Then I'm asked to also find the values of the variables, so I need the others. Well, Y would have to be 6. There's not really any work you have to show for that one because it just has to match up. For X and Z, you can kind of already look and see kind of what is it going to be, because it's just, you could just say it's 3 is turning into 1, and same thing for Z. You don't have to necessarily show work for this, but you could. If you wanted to figure out how do I show work for this, you could set up a proportion. So although the answer is just 1 for X and Z, and for, I'm sorry, I wrote this wrong. For Y, it was not 6, it was 2, because originally it was 6, but when I go to do my reduction, of course, it's 2. So I'm just like dividing each of these by 3, essentially is the same idea, or multiplying by 1/3. But if I want to show work, here's what it could look like. I could set up a proportion like X over 3, I'm matching the corresponding sides, and then I match sides that I know are corresponding also, like 2 over 6. And I just took the same rectangle for the numerator, and then the other rectangle A for the denominator, and then I can cross multiply and solve. So I could say 6x is equal to 6, divide by 6, and I find out that x is 1. So you don't have to show this work. Sometimes we're going to need to later this unit, but this one you could have just kind of said, I'm going to divide them all by 3, and kind of work through it that way. The next one, though, does get a little bit more complicated because there's an n-7 there, so you are going to need to set up a proportion and see, this one's an enlargement, and you could find the variables. I'll let you guys try these out, and I can go over them if there's questions. Same thing for these bottom ones. You know that in this case, these are quadrilaterals. They're saying they're similar, and it's saying, can you find the scale factor and find the value of Y? So again, you just have to match the corresponding sides. So look at the order of the letters. L and F match up, so L with F, and then it goes to M and G. So there's M and G at the top here. So this 12 and this 15 are matching up. Now we don't know for the scale factor, it's got to tell you from what to what. In this case, we don't know which one is the original one versus which one is the image. So you can technically go both ways on this. You could do 15 over 12 or 12 over 15. Now, generally, when we write these similarity statements, it goes original is the first one, and then the image is the second one. But really, we should be more clear, and we're going to kind of continue telling you more clearly which one is which. So if I did do, I'll do image, actually then that would be 15, over original, which would be 12. I could match those sides and then reduce the fraction. This would be 5 over 4. That could be how I could find the scale factor. Or you can use any other side. And then notice this side has to match up with this. So we would be able to figure out what that side would be to solve. x. So you could say 15 over 12, for example, and then do 40 over y minus 10 and solve that proportion using cross multiplication. Okay, and then you could find out what your answer would be for each one, or you can just, if you want to ignore the proportion, you can take your scale factor and use that to help you find the missing side. Just be careful with the order, because 5/4 has you going from the image to the original. So if you want to go from original, just make sure, again, you're multiplying by the correct number. Okay, and so when you get an answer here, that'll be your y. And finally, that last one is another same thing. You can just work with angles this time. All angles are the same in similar polygons. So it says write a similarity statement and find the similar scale factor. But you can still do that to find the missing side length. There's, I think all of the side lengths are there. You just have to find the scale factor, so you just have to match up your sides. So for example, 8 matches up with 14. 12 matches up with 21, because you have to look at the sides that are, I know it's oriented differently, but they're the sides that are creating the right triangle, and make sure the smallest ones match, whereas the biggest ones can match. That all would give you the exact same proportion. In this case, if I divided top and bottom by 2, I'd get 4/7. This one, if I divided top and bottom by 3, I'd get 4/7, right? So 4/7 is my scale factor, right? Which I don't know for sure, though, if it says if they are similar. We don't know if they are similar yet, so you would have to first match everything and check to see if the corresponding angles are congruent or not. So far, I know this is 90 degrees, that's 90 degrees, and then this angle here is 144. And so I could technically solve for x that way, but in order to know if this works or not, I need to find out what x is. So if you add up all of these angles and set them equal to 360, because that's what we have, a quadrilateral here, that's how we're going to check to see, do we actually have what x is equal to, and does it equal the same number when I substitute it in for this angle? Will it be the same? So for example, once you do this work, I'll just kind of, to save time, say what it comes out to. It comes out to x is 54. But if x is 54 and you, let's say, substitute it in right here, you're going to get an answer here which is 108 degrees. Since this letter M is supposed to correspond to C, these are the same angles here, because you can see the 14 and the 14, the 8 and the 8 surrounding it. Those angles are not the same. One is 144, one is 108, so these are not similar. And you can see that because the corresponding angles are not congruent. All right, and that's going to be kind of where we stop. There's the other ones that we kind of skipped here. You can definitely try out some more for some more practice, and I'll go over the 7.1 homework tomorrow. But go ahead and try the 7.1 homework out for the rest of the time, and try it out tonight. So, or at least, I'm sorry, we're not going to go over it tomorrow. We're going to go over it on Thursday. But bring that 7.1 homework with you on Thursday. All right.